OK, so whenever we learn about a data structure, we learn what it is, what it does, why it's useful. And then usually what we do is we discover there's already somebody who wrote it for us in the Stanford libraries. And that's also true here. And we're going to play around with the Stanford version of the graph and see what it can do. And then after we're kind of a little bit familiar with that, the next step is we start talking about, well, you know, what is in there? How do you build a graph? How would you create a graph if there were no Stanford library to help you along with that? There's a chair back here that I need to grab. So let's talk about the Stanford implementation of a graph class. There's a class in that library called BasicGraph. By the way, you guys notice I try to stand in the white part of the slide here? There we go. I can't move from this spot. There's a class in the Stanford library called BasicGraph. There's also a class in the Stanford library called Graph, but I didn't like it. I thought it wasn't basic enough, so I wrote another one called BasicGraph. So that's the one I'm giving you guys. You could use the regular graph if you want, but mine is more basic than theirs. So you include BasicGraph.h, and then you can create a BasicGraph object, and now you can add a vertex to it, or you can add an edge to it. When you add a vertex, you have to give it a name, which is a string. You have to. And then when you add an edge, you specify the names of the two vertexes that it connects. This is a directed graph library. So if I add an edge from A to C, it makes an arrow out from A that touches the arrowhead at C right here, from A to C. If you want an undirected graph, or you want the edge to go both ways, you just add the edge twice, once from B to C and once from C to B. That's what the code does right here. And then I end up getting essentially an undirected edge there, or close to it, basically. OK? So that's how the library works. Fairly simple. It doesn't provide too much, because we want to leave some out so that you guys will write some of this too. But here are the members, the functions that the graph library provides. You can construct one. You could add edges, add vertices. You can clear them out. You can remove vertices and edges. There's also methods called getNeighbors, getEdgeSet. It basically allows you to ask, what vertexes can I reach by an outbound edge from this current vertex? OK? That's mostly what we have. There's a toString, and there's a size. And just most of the stuff you would kind of expect it to have is what it has. And one thing that isn't really specified very clearly right here is when it says, how do you get the neighbors of like a vertex V, or this kind of stuff? What type is V? Well, you can pass the string for the name of the vertex, but the graph also has inside of it these structures. These little structures called a vertex struct and an edge struct. And what happens is, like, if you're actually building a graph, you end up wanting to store information about these different vertexes sometimes. The main thing I want you to see is that they have a name and they have a structure of edges, and the edge has a start and a finish. They're represented as pointers. And so, like, if you ask the graph to get a vertex, like we added earlier, we added a vertex called C. If you want to talk to that vertex and learn about it, you call this method getVertex, and you pass in the name, you pass in C. It returns you a vertex star, a pointer. You're basically getting a pointer to some internal structure inside of the graph. And now what you can do with that thing is you can talk about all those things. You can talk about all the neighbors, all the edges. And so typically what you do is you say, well, I want to know all the neighbors of this, and I want to mark them as visited, or I want to do this. You can do things to all the properties of that vertex by talking to that vertex pointer. So sometimes those structures are useful. You don't always need them, but that's kind of how you talk on a more detailed level to each vertex or to each edge. I think it's easier to understand through an example. So I have a little example program that I want us to write. We talked a little bit about social networks like Twitter. Imagine that we have a data file full of lines. Each line has a pair of strings. And the strings are two names or two usernames in Twitter. And so it'll say, like, Marty Scarlett. And that means Marty follows Scarlett on Twitter. And so we're going to read in all those lines. And I want to report out who in that data file has the most followers of followers. So direct followers would just be people that directly follow you. And followers of followers means, like, how many people follow your followers? If Marty follows Scarlett, how many people follow Marty? Those people are Scarlett's follower of followers related to me. Ugh. Anyway, I want to find out who has the most such people. You might say, why would you want to know that? That's an artificial sort of a thing to want to know. What, can you imagine? Like, I mean, if I want to know how cool Scarlett Johansson is, don't I just want to know how many followers she has? Why would I care how many followers of followers she has? What does that mean exactly? just like in real world Twitter terms. What does that mean? Yeah.
It would mean the amount of social influence every follower of Scarlett Johansson.
Yeah, you said the amount of social influence that Scarlett's followers have. I would say, like, if I have a bunch of Twitter followers, but all my Twitter followers are lame people who don't have any friends, then even though I have a lot of friends, none of my friends are cool, really. You know what I mean? It's like, it's not just that you have 1,000 followers, it's that your 1,000 followers are influential, cool people who themselves have a lot of followers. Therefore, my friends are better than your friends, and I'm cooler than you. That's kind of how it works, right? So, I mean, this is a little bit of an arbitrary problem, but I just want to try playing with this graph library to calculate this particular piece of information. Now, I will concede willingly you can solve this problem using other structures. We could solve it with a map or different other things. And I'm not saying it's impossible to solve without a graph. I just think that the solution with a graph is elegant, so we should try to write it that way. So let's go to the Qt creator here. And I've got a file called graph main. And I've got a prototype called coolest. And I'm going to pass it this twitter.txt, and then I want to see who it returns out as the coolest person ever. And if you want me to just show you that input file, twitter.txt, just so you can picture the input, I mean, it's a pretty simple input format. It just looks like this. You know, Stuart follows Marty, and Helen follows Elmer, and just all this kind of stuff, okay? It's a small file just so we can kind of trace through it more easily, but you could imagine it being a much bigger file. Okay. So how do I figure out who's coolest? Well, I think the first thing is we got to read the data out of this file. So maybe let me set that up a little bit. Why don't I say we need an if stream of input, and we'll open this file name. And I'm going to assume the file exists and stuff. You know, it'd be safer to check that, but I'm just going to assume it exists. Now, this thing has these lines like, you know, Stuart follows Marty. Like, that's the examples of the kind of lines we're going to read. I think we could read this sort of a word at a time, like a token at a time. So maybe I'll do like string name1 and name2. And then to read, I could just say while the input is able to read name1 and name2. You know, that's like, you could use that syntax to like pull out from the stream 2 tokens at a time, 2 words at a time. While I'm able to do that, there are more lines left in the file. So what should I do with the data as I read it? I'll give you a hint. It has something to do with a word that rhymes with giraffe. Draft. Use a draft? That's interesting. You know, in like improv, they tell you never to say no. They tell you to say yes and, right? Have you heard that? So, yes and we'll use a graph. So we'll make a graph, like a basic graph, let's say. But like maybe you could tell me, be more specific, like what do I do with the data in terms of the graph? How does the data get put in the graph? Do you have a suggestion?
Maybe you want to add name1 and name2 as vertices and then put an edge.
Right, so just to be clear, Stuart Marty means Stuart follows Marty in Twitter. So what she said was great. She said those 2 words, those 2 names are both like users of Twitter. So we should make sure that the graph has them as vertexes and add them if it doesn't. And also now there should be an edge between those 2 people in the graph, right? So we can do graph.addVertex name1. And we can also do graph.addVertex name2. And then we can do graph.addEdge from name1 to name2. You might have questions like, well, what if we didn't do this and just went ahead and directly added the edge? Would it notice that those names were not in the graph, and would it automatically add them? I think a lot of the methods get angry and crash if you try to like use them with vertexes that aren't declared and stuff. And you might wish it were different, but I think this helps you catch bugs sometimes where you pass in the wrong vertex and you kind of don't want it to add that vertex. You want it to halt the program. You know, that's the design of the library. So, okay, we add the edge between the people. Now when we get down here, supposedly we have a graph full of this information. Maybe that's a good point to just see if it's working. Let's just see out the graph, endl, okay, and see if it got in there at all. So I'll compile and run, and kablam, node Marty already exists. Oops. So what happened? Well, the reason that it did that was because I think we're trying to add Marty more than one time, right? Do you know why we would be adding Marty more than one time? It's weird to talk about myself in the third person, but Marty's okay with that, I guess. But like right here, I'm the name 2 on 2 of these lines, right? So I'm adding Marty a second time. It doesn't like it when you try to re-add a vertex that already exists. Okay, we can fix that, right? Like, what do you think I do to avoid that issue? I could pop up what the graph can do. Do you want me to show you that? Oh, I guess this doesn't list everything, does it? Some of the methods are missing. Well, let's type graph dot. So there's a bunch of good stuff in here. Yeah, why don't we just see if the graph contains the vertex for these people, right? Like if it doesn't contain vertex of name 1, we'll add name 1, right? And the same thing for name 2. Yeah, my slide doesn't have every method. Unfortunately, the graph has like 50 methods, and so it's kind of hard to list them all. Maybe I should add some of those, though. And then this edge, I think the edge one, like you might ask, we could check if it contains an edge already from name 1 to name 2. But I think if it already did, that would imply that this file was bogus. And maybe it would be. But let's assume, I guess, that the file's OK for now. And it doesn't have duplicate lines that have exactly the same people on them. So let's try again. And I print. And it's a little hard to read. But what the printout of a graph does first is it prints all the vertexes first. And then it prints all the edges, like that's an edge, that's an edge, that's an edge. And I guess if you want to know if it's right or not, you'd probably want to see the file. I think it's a little hard to compare because the file's kind of randomly written, and this thing kind of prints out in alphabetical order. But it says there's an edge from Donald to Marty, and there's that edge right there. And it says there's an edge from Donald to Stuart, and there's that edge right there. Yeah, I think it's working. I think we have the graph storing the right stuff in it. And of course, we don't know quite how the graph is implemented, but I think our assumption is that these methods are reasonably efficient, and there's somebody clever came up with how to write this. Not me, but somebody, made this fast enough. We don't have to feel bad calling these methods. They're not slow. So now we have a graph, and now our goal is to find the coolest person, the most followers of followers, right? How do we figure that out? Well, OK, let me change the question into a simpler question. How would we figure out who just has the most followers? That's easier, right? But maybe doing that would be close to what we're actually supposed to do. How do you know how many followers a person has? What do you think?
In degrees?
Get the degree of the in degree of how many arrows are pointing at that person, right? OK. So now, one thing that I like this problem because it sort of trips people up. Like, your answer is very good. Some people see this list of methods and they go, oh, I want the neighbors, right? The people who are your neighbors are your followers, right? Is that true? What does it mean for you to be, like, if A has a neighbor called B, what does that mean? A follows B. So A's neighbors are not the people following A. That's the people who A follows, right? After the right direction here, you know what I mean? Like if I want to know how many followers Scarlett Johansson has, those are not the get neighbors of the Scarlett Johansson vertex, right? OK. Well, one thing you can do with a graph that might be useful to know about is you can do for each loops over the graph, which gives you for each over all the vertexes. So you can say for each vertex star v in the graph. You can actually do that. That will loop over each vertex, and it will call that vertex v as it visits the vertex. Now, this is that weird structure thingy, that weird pointer thingy. And we were trying to kind of get familiar with that. I could just do something like cout vertex colon v arrow. These are all the different thingies inside of a vertex. But the main thing you would do is you might want to print its name. So like if I ran that, it would print like vertex Bruce, vertex Donald, vertex. So the like strings that I passed in when I said add vertex, those end up being the like name field of the vertex objects inside of the graph when I loop over this thing. Any ideas? Yeah?
For each vertex, you can get the set of, there was some function. It's like get set of, get edge set.
Okay, get edge set.
That gets that's all the edges that start at, they start at B, that's a problem. Want the other direction. Okay, get back.
Yeah, it's tricky, huh? Darn 106B, the tricky graph problem. Did you have a suggestion? Yeah.
What if you switch the edge so you do like from name 2 to name 1, and then your get neighbors are the people who are following you, and then you get the neighbors, like, and then for each of your neighbors you get the neighbors, and then you add that to your followers, and you have some sort of like math.
I really like her suggestion. What she said was, well, okay, so we've got this graph where the edges point the wrong way. Do you understand that? Scarlett Johansson vertex has a bunch of edges that point out to the people Scarlett Johansson is following. I don't really want that. I want a bunch of edges pointing at Scarlett. I want to know who is following her. That's what I want. And so my edges are kind of telling me the wrong thing. In terms of this graph library, what it gives me is who do I point out toward, right? And the way I've built my graph is kind of, the edges are kind of backwards versus what I really wish I had. And what she said was, well, we built the damn graph. Why don't you just flip the edges around so they're that point the other way, so that the edges going out from Scarlett really do go out to the people that are following Scarlett. We could make the graph do that, even though intuitively, if you think of the social graph, you think of it as the way we already have it. For solving this problem, doing it the other way might be better. So I think that's actually a really insightful suggestion. So maybe instead of an edge from name 1 to name 2, why don't we make an edge from name 2 to name 1? Now the graph really means sort of is followed by, you might say, instead of follows. It's more of a passive edge instead of an active edge. So now if I loop over vertices, the edges here, the neighbors here, really are the followers of the person. If I wanted to know something about Scarlett Johansson, I could say graph.getNeighbors of V. Those are that's going to return if you see this thing here, it returns a set of pointers to the neighbors of V. So if I just wanted to know how many followers Scarlett had, I could just say the dot size of that set. That would be like how many followers Scarlett Johansson has now. Okay, but I want to know how many followers she has. Well, maybe I'll just do it this way for the moment. Int followers equals that. So let's do, if we want to know who has the most followers, I think somebody else was saying, well, we just need to do a loop that kind of gets the max of all such things. So int max equals 0. And maybe the person with the max, we have to keep track of what their name is because that's what we're returning at the end. So if this number of followers here is bigger than the max I've seen so far, then I'll say max equals followers and max name equals the person's name that I'm at right now, which is called v name. Okay? So this currently is close to solving the problem. It's really telling me who has the most followers. Oops, a string is not an int, sorry. There we go. Coding is hard. Okay, let's run it again. So it still says the coolest person is an empty string, but that's because I returned an empty string. I should return the max name. That's a darndest thing about computers is they do what you tell them to, right? So it says the coolest person is Elmer, but I know that's not true. I'm friends with Elmer. I know that's not true. He's a good guy. But I really wanted the followers of followers. So like really the number I wanted wasn't just the neighbor size, right? How do I get the number of followers of followers? Do you know? I think I called you a couple times. Let me see if I can get somebody new. What would you do? Yeah.
I loop over the neighbors of V and then get the number of neighbors they have.
Loop over the neighbors and ask for their neighbor count. Right. So really what I'll do is instead of doing just my neighbor's size, I will say start at 0 and then do for vertex star neighbor in graph get neighbors of V. For each of the neighbors, I want to know how many followers they have. So let's do followers. It's really followers of followers. Equal or plus equals graph.get neighbors of the neighbor dot size. Because the graph get neighbors of neighbor is the set of people who are following the neighbor. I want to know how many people are in that set. That's how many followers the neighbor has. I add up all such things, and that tells me followers of followers. So this whole max behavior here is still valid, so I'll leave all that. I compile it, and oops, what happened? Graph, it shouldn't be graph arrow get neighbors, graph dot get neighbors. Graph is not a pointer. Graph is an object. Sorry. Compile and run. And now the coolest person ever is Mehran Sahami. I know that for a fact. He's just awesome. So that's, for this data set, that turns out to be the right answer. You can go through the data later and verify it. Anyway, that's a taste of graphs.